Okay, hi everyone. Good morning to all of you. I hope I am audible. So, in yesterday's lecture, you have seen I have discussed about the recycle, bypass, and purge, all of these concepts. But today also I'll be talking about some deep concept about the recycle, bypass, and purge. And after that, we'll move towards the crystallization process. So, yesterday, what I was discussing about the single pass conversion and overall conversion. So, sometimes get used to ask about the questions from the single pass conversion and overall conversion. So, you can see this question 56 is based on the single pass and overall conversion. Let's see how we can solve this kind of question. So you can see here the reactant M is converted into product N, right? So the reaction is happening here. M is going to get converted into product N, right? So this one is the reaction. And the presence of catalyst in the fixed weight reactor, all the flow rate Fg, Hp, and R in moles per second, and mole fraction of reactant M is in the these stream are except as you are shown in the figure diagram, the overall conversion is, see, one thing is that this one is the reactant, right? So this one is the reactant, which is in the feed. This is mixed feed. This is fresh feed, right? So yesterday I have discussed, this is your fresh feed. This one is your mixed feed. And this is your mixed product. And this is your final product, right? So whenever you are supposed to calculate the per pass conversion. So per pass conversion will be based on the mix feed and this product. So what questions they have asked? Overall fractional conversion they have asked. So what I'll tell you, the overall fractional conversion, X overall can be written as a feed. This is feed. So fresh feed F into XF minus product is P into XP divided by based on the fresh feed. Is that clear? F into XF. Is that clear? This is your single pass conversion, sorry, overall conversion. Now, when we talk about the single pass conversion or per pass conversion, so there may be single pass conversion or it can be called as per pass conversion. That can be written as mixed feed minus mixed product divided by, I mean, that is based on the reactor entry. So this will give you the per pass conversion. So you can understand these things how I am writing Z into XZ minus H into XH divided by Z into XZ. Is that clear? Okay. So here, based on these particular questions, the option will be the option D will be correct answer. Is that clear? Is there any doubt in this? How we are writing the single pass conversion and per pass conversion, right? This is very, very important. So whenever we talk about the single pass conversion, so let's say this one is the reactor and this recycle stream is coming something like that. So this fresh feed is going and this one is your mixed feed. This one is your mixed product and this one is your final product. Is that clear? So X overall can be written as fresh feed minus final product divided by fresh feed and X single pass that can be written as mixed feed minus mixed product divided by mixed feed. So, I mean, the question that has been asked here, you can see this was only based on the formula. But again, if any questions are coming from this concept, you are supposed to calculate some numerical question answer, right? Okay, after that, I'll be moving towards the next concept here, right? So this one is the another question that ammonia NH3 oxidation process occurs. So one of the most important thing is the reaction. So whenever in chemical technology, these questions can be asked that ammonia is oxidation, ammonia is getting oxidized, it is going to form nitrous oxide and 6H2O, right? So the reactions can be written as obviously your NH3 plus O2 is getting converted into 6H2O plus NO. So first thing I told you, whenever you are solving any reaction-based question, you have to balance the reaction. So 4NH3, 5O2, 6H2, and here there will be 4NO. Now reaction will balance. Air is supplied such that oxygen is 20% in excess of that required for complete conversion. So this reaction would be happening in a reactor, right? So your feed will be your ammonia and air. And they are telling you in air oxygen will be there and obviously nitrogen will be there, right? And the product is going to get formed here you will supply feed and product will be formed, and here you will see H2O, here nitrous oxide will be there, some oxygen will be there, and maybe unconverted NH3 will be there, right? All of these things can be there, and this reaction would be happening here in this particular reactor. Okay, so they are asking you to calculate the mole fraction of oxygen in inlet gas mixture NH3 plus air. So here you are supposed to calculate mole fraction of oxygen. So NH3 is there and oxygen is there, nitrogen is also there. So you are supposed to calculate mole fraction of oxygen in inlet gas mixture. So X of O2 in feed is what you don't know what is these things, but let's try to calculate this thing. But they are telling you air is supplied such that oxygen is 20% in excess of that required to complete conversion. So I mean the amount of air which is being supplied here, that will contain 20% more air that required for the complete conversion of NH3 into this NO. Is that clear? So let's see how we are going to solve this kind of question. Hmm. So if I'm talking about air contains 79% of nitrogen and 21% of oxygen, right? And how much, okay, first thing. Second thing is that if you see the reaction that 4NH3 plus 5O2 is getting converted into 6H2O plus 4NO. So if NH3 has to be completely converted into the product nitrous oxide, then how much air will be required for 1 mole? Or let's say I'm assuming 4 moles of, let's say 4 moles of mm, NH3 is there in the feed. So I am assuming 4 moles of nitrous oxide and ammonia is there in the feed. So how much oxygen is required? So O2 required, this is also called as O2 theoretical, that is equals to 5 moles, right? But how much O2 is being supplied? 20% extra. O2 supplied. Okay, sorry. Since we are supposed to calculate theoretical amount of air, so how much air is required? Theoretical air requirement now you'll calculate. So this is theoretical oxygen requirement. So 5 divided by 0.21, right? 21% oxygen will be there in the air. So that will give you 23.809. So you have calculated theoretical air requirement. So extra 20% of air is being supplied. So actual air supplied will be 1.2 multiplied with how much? 23.809. So that will give you 28.571 moles of air. So that much extra air is being supplied. Actually, I mean, sorry, that much air is being supplied actually throughout the reaction, right? Now, so what is the inlet composition? So air is there, that much amount of air is there, 571, multiplied with how much? 0.21. Is that clear? So just try to calculate this and tell me how much air is there. So I think once you will multiply these things, you will be getting 5.991. Sorry. First, I have to calculate for oxygen. Right. So inlet composition O2. O2 will be this one. What is N2? Since total air is this one, 28.571. Now multiplied with 0.79. How much this will be? 22.5714. You have calculated oxygen composition. You have calculated nitrogen composition. How much ammonia was there? NH3 was there in 4 mole. So you are supposed to calculate the mole fraction of oxygen now. So X of O2 will be equals to what? Number of moles of oxygen, divided by total number of moles. Oxygen plus nitrogen plus ammonia. Is that clear? And total number of moles will be 28.571. That is 5.991 divided by 28.571. So once you will calculate these things, you will be getting 0.18420. Something like that. Is that clear? So basically what I did in this particular problem, we calculated how much oxygen, how much air is required for the complete combustion, right? So we know from this particular reaction, if I assume 4 moles of NH3 is there, then 5 moles of oxygen is required. But how much air is required, I have calculated. So since air contains air multiplied with 0.21, that will give you 5. So how much air will be there? 5 divided by 0.21. So we have calculated number of moles of air, right? So actually, how much air is being supplied here? So that is there. Theoretical air requirement was this, but they have told you that 20% extra air is being supplied, which contains oxygen that will, create complete combustion, or that will give the complete combustion. That's why we are doing this particular calculation. And after that, once we get to know about the actual air supplied, again, composition of oxygen and nitrogen is not going to change in the air, right? Composition will be same, that is 21% and 79%. And based on that composition, we can calculate the actual number of moles of all of these gases that is required for the, so that is oxygen, nitrogen, and ammonia. And after doing that thing, you can calculate the number of moles as well. Is that clear? Yeah. Okay, then I am moving towards the next question of today's discussion. And that question, this question has been asked in GATE 2025, sorry, 15. And this is also based on the recycle and purge. So you can see the question, first try to read the question. So in the question, you can say, they are telling the schematic diagram of a steady state process is shown below. The fresh feed app. So here the fresh feed is there, to the reactor contains 96% of A. So this contains 96% of A and 4 mole percent of inert. The stoichiometry of the reaction is given. A is getting converted into C. So A is the reactant and C is the product. And a part of this recycle reactor effluent is recycled. So here you can see this is a recycle. The molar flow rate of recycle stream is 0.3 F. So recycle stream is 0.3 F, where F is the feed stream, right? So a relation has been given to you for recycle stream and feed stream that you have to understand. Now, after that, the product stream P, this is the product stream. You can see here. This one is the product stream, and this contains 50% of C. This contains 50% C. That is the product. The percentage conversion of A in the reactor, the percentage conversion of A in the reactor based on A entering to the reactor at point A, based on the A. So this is they are I mean you are supposed to calculate the percentage composition based on the number of moles of A which is entering here at the inlet of the reactor, right? So let's try to understand how we will solve this thing. So what will be the percentage composition? Percentage conversion of A will be, let's say if I'm assuming this point is 2, right? So this point is 2. So percentage conversion of A will be equals to what? Number of moles of A at point 1 minus number of moles of A at point 2 divided by number of moles of A at point 1. This is the percentage conversion of A. So by any means, if you are able to calculate the number of moles of A at all of these points, at point 1 and point 2, the question will be, you will be able to solve the question. So what I am assuming here, let the basis, that means F is your 100 moles. This feed I am assuming is 100 moles. So what is A in feed? That is equals to 96 moles, and inert in feed will be how much? 4 moles, right? So at this particular conditions, we get to know what is number of moles of A and what is number of moles of B. So if I do the overall balance, so if I'll do the overall balance, what you will see, so F will be equals to P, which is equals to 100. So total amount of feed which is entering into the reactor, at the at the end you will be getting the same thing. So if you want to do the overall balance, you can use these things. So this is one thing. So this feed is coming here, and this things is coming, and one product is going like that. So whenever you want to do the overall balance inside this envelope, you will be putting everything. That's it. So here feed is coming and here product is coming. So directly F will be equals to P if I am assuming this overall balance in this particular envelope. So you can write that F is equals to P, which is equals to 100 moles, right? So in product stream, you see that C is equals to 50%. That means F P is your 100. So that means C will be equals to number of moles of C will be equals to 50 moles. Is that clear? We get to know these things. And one more thing is that you can see the fresh feed of a reactor contains 96% of A and reactant A and 4 mole percent of reactant at the inlet. Okay. So C we get to know. So here, out of now, how much moles are remaining? Remaining will be 50 moles. So how much A will be there? A will be obviously 46 and inert will be how much? 4. Why? The total amount of feed, uh, inert in the feed will be equals to the total amount of inert in the product only, right? So if I want to write F multiplied with inert, that is, let's say F is 100, 100 multiplied with 4 divided by 100, that will be equals to P is also 100 multiplied with inert, right? So how much inert is there? Inert will be equals to, percentage of inert will be equals to 0.04. Is that clear? Percentage of inert will be 0.04. But now, here you can see that 50 moles is there, only the remaining will be 50 moles only. Is that clear? E into I. So basically what I am trying to do, just try to understand. 4 moles of inert was here. So 4 moles inert will be here only. So the out of 50, 4 moles went to inert. So what? How much A will be there? So only 46 moles of A will be there. So till now what we have seen in feed, we have seen feed E will be 96 and inert will be 4. In product E will be 46 and inert will be your 4. Right. Now just try to understand. One more thing is that so here we are supplying 96 moles of A, and in here we see that number of moles of A is 46, right? Only 46. So what is mole fraction of A here? Mole fraction of A will be 0.46. Is that clear? So the same mole fraction will be also mole fraction of A here in the cycle stream will be 0.46, right? So how much A is entering here? That is 0.3 F multiplied with 0.46. That is equals to 0.3 multiplied with 100 into 0.46. Is that clear? So that will give you 13.8. So basically what is happening here, just try to understand. This is the reactor, and again I am making, this is a separator, something like that. So this is the product stream. This is the recycle stream, which is coming here, and this is going. So this feed is there. I am now writing only for A. A is 96. How much A is coming from here? We have seen that is your 13.8. 13.8 is coming here. How much A is going here? Is your 46. Is that clear? So you are supposed to calculate the overall conversion. Sorry, single pass conversion for this particular thing. So total amount of A which is entering at this point is how much? A number of moles of A at point 1. This is our point 1. This is our point 2, let's say. So how much? 96 plus 13.8, that is equal to 8, 109.8 moles. So at this point, number of moles of A we have calculated. So the first thing. Second thing is that from the stoichiometry of reaction, A is getting converted into C. So number of moles of product form is 50. So number of moles of A reacted would be also 50. Is that clear? So what you can say, number of moles of A reacted will be also equals to 50. So directly we have calculated X A, that is conversion is equals to number of moles of A reacted divided by number of moles of feed multiplied with 100. So number of moles of A reacted is 50. Directly we have calculated. Number of moles of A in feed is 8 into 100. Once you will calculate, it will give you 45.5%. Is that clear? So is there any doubt in this? You are asking me to NA1. Okay. See, one thing is that what I am trying to tell you. So this is your reactor, and this was your separator, right? Try to understand. So we know this is a product stream and a recycle stream is coming here to the reactor, right? This was feed. In feed, number of moles of A in feed is how much? 96, right? And here you have seen recycle stream was 0.3 F. So what is 0.3 F? 0.3 into 100. Is that clear? So that is equals to your 30. Is that clear? And the mole fraction of A here, XA at this point will be equals to XA at this point, mole fraction of it. Is that clear? Why? Because both of these streams are coming from the same separator. So some part is going here and some part is going here, but the mole fraction will be same, right? So here what we have got, number of moles of C was 50, number of moles of A was 46, and number of moles of inert was how much? 4. So what is XA? XA was 0.46. That is number of mole fraction of A. So obviously XA here will be also 0.46. So how much number of moles of A which is coming here? That is equals to 30 multiplied with 0.46. Is that clear? 30 multiplied with 0.46. So that will be equals to 13.8. Right? 13.8. So here if you see a reaction is getting converted to A into C and C at this point is your 50. So how much A is getting converted? For 1 moles of C, 1 moles of A is required. So for 50 moles of C, 50 moles of C will be required. So number of moles of A reacted will be equals to how much? 50. And how much A is entering here? So that is equals to how much? 96 plus 13.8. That is 109.8. So number of moles of A at the reactor entrance is this one. Number of moles of A reacted is 50, right? Directly. That is the fractional conversion thing. So fractional conversion will to what? Number of moles of A reacted divided by number of. So this is the point one where you are asking to calculate total number of moles of A, right? I hope this is clear to you now. Clear to you now. Number of moles of A at reactor inlet, that is equals to 3 divided by 109.8. This is fractional conversion. If you want to calculate percentage, you have to multiply with 100. Is that clear? Okay. Okay, great. So this is all about your recycle reactor, all of these things that I have discussed right now. And non-isothermal thing already I have discussed this kind of concept in your chemical reaction engineering. So I'm not going to discuss that non-isothermal thing here. Percentage conversion, again, these kind of questions can be asked. So you should be ready with all of these concepts. So very small topic that has been left here, that is your crystallization. So let's see if we can start the crystallizations here. Okay, so right now I'm going to talk about the crystallization. So I think last 2 to 3 years they have not asked the questions from the crystallization. So it may be this year there may be a possibility that these questions can be asked. So let's try. This is very small concept, but it'll complete in very small time. So first let's try to discuss. Definition I am not going to discuss here. So what will happen as we are going to decrease the in crystallization generally what happens, just try to understand, as we are going to decrease the temperature of any solution which contains solute and solvent. So what will happen, solubility of solute in solvent goes on decreasing, which results in formation of hydrated crystal, which results in hydrated crystal with remaining solution called mother liquor, which is in equilibrium. Right. So generally what is happening, just try to understand. Let's say if there is any crystallization unit, so you are supplying a feed which contains a solution, right? So if I'm assuming mole fraction of solute in the feed is XF, so if you are decreasing the temperature, what will happen? It is going to form a hydrated crystal. I'll be denoting it as C, and there will be a formation of mother liquor. This will be in M, and here mole fraction of the solute will be XM, and here mole fraction will be XC, and there will be a water evaporated W. Right. So when there is a water, definitely there is not in water only there is no solute, right? So solute will be either in hydrated crystal or mother liquor, right? That's why we are removing the water. So here what you can see that F is your feed flow rate, M is your mother liquor flow rate, C is your crystal crystal amount, right? Something like that. So if I'll apply the balance, so what you can write, F is equals to C plus M plus W. This is your equation first. And second one, apply solute balance. So F into XF, that is equals to C into XC plus M into XM plus W into XW. So XW, I mean amount of solute will be 0 in the water. That's why XW will be 0. XW will be 0 because no solute will be there in water or vapor, right? So you can say directly F into XF, that is equals to C into XC plus M into XM. Is that clear? These things directly. Is that clear? Okay, so let's try to solve one question. How we can solve this kind of question. Just 1 second. Let me share the question first. Okay, so try to read the question. I'm giving you 2 minutes, and after that, I'll solve this question, right? Yes. Okay, so see what sorts of thing that has been written in the problem. So aqueous salt solution enters a crystallizer, right? Operating at a steady state at 25 degrees centigrade. The feed temperature is 90 degrees centigrade, and the salt concentration is in the feed is 40% by weight, right? So the salt crystallizes as a pentahydrates, and the crystal and the the crystal and mother liquid leave the crystallizer. The molecular weight of the amount in hydrous salt is 135. The solubility of salt is 28%. The feed flow rate required for a production rate of 100 kgs of hydrated salt is. Just try to understand. This question is very, very important. So this question has been asked in GATE 2020. So let's say we have a crystallizer. We have a crystallizer. So feed will be entering here. So feed flow rate is not given to you, and there will be a crystal formation, hydrated crystal form. This is a mother liquid, and definitely there will be a water vapor. So they are asking you the feed temperature is na, and the salt concentration in feed is 40%, right? So here salt concentration is 40%, XF is your 0.40. The salt crystallizes as pentahydrates, right? So let's say if any salt is there, so this is going to crystallize as a pentahydrate. So any salt dot 5H2O will be there once it will get crystallized, right? So this is the salt and five water molecules will be there. That's why this is called as a pentahydrate, right? So okay. The crystal and the mother liquid leaves the crystallizers. Crystal and mother liquid leaves the crystallizers. So water vapor is not there, right? They are only telling the crystal and mother liquid. So water vapor is not there in the picture. The molecular weight of anhydrous salt is the salt which is here having molecular weight is 135. This is anhydrous form. If water is not there, this is anhydrous form, right? So if you want to calculate the molecular weight of total hydrated salt, so this is molecular weight of anhydrous salt plus 5 multiplied with 18. That is molecular weight of water. So you can calculate the molecular weight of hydrated salt also, right? This thing. The solubility of salt at 25 degrees centigrade is 20%, right? So whenever they are talking about the solubility of salt, so this salt will be soluble in mother liquid. So XM. So Xm will be equals to 0.20. This is your solubility. Always remember. Solubility means the mole fraction of salt in the mother liquid. That's it. Right. So Xc is not given to you, right? Okay, here Xc is not given to you. So we'll calculate Xc. What will be the value of Xc? See. So now what will we calculate? Molecular weight of hydrated salt. That will be equal to molecular weight of anhydrous salt plus 5 multiplied with molecular weight of water. These things you would be knowing from class 12 only. This is 135 plus 5 multiplied with 18. So this will give you how much? 135 plus 90. So 225. Is that clear? So now we want to calculate Xc. Xc will be equal to what? So molecular weight of anhydrous salt divided by molecular weight of hydrated salt. Why? Because in crystal you will see some water vapor will be there and salt will be there. So water vapor plus salt. So we want to calculate the molecular mole fraction of salt. So that will be salt divided by total. So that is equals to 135 divided by 225. That will give you 0.6. Is that clear? So we get to know Xc. We have Xf that is equals to 0.40. And we have one equation F is equals to C plus M. F we don't know and C and M is given to you. So let's try to understand. The feed flow rate required for production rate of 100 kgs of hydrated salt. So means C is given to you. C is your 100, right? C is your 100 plus M. M is not given to you. Now, if I'll do the salt balance, F into XF that is equals to C into XC plus M into XM. F is not given to you. XF is given to you. How much? 40%. C is 100. And what is Xc? That is equals to 0.6. Thus, M is also not given to you. And what is Xm? 0.2. This one is our equation first. This one is our equation second. Okay. So, sorry. This one is equation first. This one is equation second. So, from here, what we can write? M that will equals to F minus 100. Right. So, directly we can write now F into 0.40 that is equals to 60 plus F minus 100 into 0.2. So 0.4 minus 0.2 into F that is equals to 60 minus 20. 0.2 F that is equals to 40. So F will be equals to how much? 400 divided by 2 that is equals to 200. So you have got feed flow rate is equals to 200. So here you will be having 200. This is your answer. Is that clear? In kg per second. So you can see either if they are asking you in mass flow rate, you can use kg per second. If they are asking you in molar flow rate, you can use in mole per second. But you have to divide these things with the molecular weight of the salt also. Something like that. Is that clear? Is there any doubt in this question? Okay, so let's try to solve one more question. I'm not going to solve this question, but yes. This is very simple question. This is not very tough. You will be able to solve this problem. Okay, so just try to solve. So here you can see that 80 kg per second, 80 kg of Na2SO4 having molecular weight is 142 is present in 330 kg of an aqueous solution. Just try to understand what sorts of thing that has been given here as data. So a solution is there. So in this solution, Na2SO4 is there and some solvent will be there because aqueous solution. So water will be there. Na2SO4 is your 80 kg and 330 kg of an aqueous solution is present in 330 kg of aqueous solution. The total weight of aqueous solution is 330. Right. Just try to understand one thing. Na2SO4 plus H2O. If you mix these things, then that will give you aqueous solution. And they are telling you weight of this aqueous solution is your 330 kg. Is that clear? And weight of Na2SO4 30 kg. So what is mole fraction of Na2SO4? That is weight of Na2SO4 is 30. Sorry, this is 80, right? Divided by how much? 330. So that is your 8 divided by 33. This is a mole fraction. So I think this is clear to you now that how you can calculate this mole fraction in the field of salt, right? Now, so after doing that, you can see, and the solution is cooled such that 80 kg of Na2SO4 dot 510H2O decahydrate crystals are going to form. So here will be C and obviously Hc and M and Xm will be there. And the solution is getting heated, cooled. So the weight fraction of Nu2SO4 in the remaining solution is, they are asking you to calculate the weight fraction of Nu2SO4 in the remaining solution here. Right. So see one thing. So here Xc decahydrate is getting formed. So the screen is not visible. Oh, just one second. Right. Now is it visual? Okay. So F has been given to you. How much? Total F is 330 kg. What is XF? XF is given 8 by 23. Right. And next thing is that what is Xc? Xc is, I have told you, weight of Na2SO4. See which crystal is getting formed? Crystal formation is Na2SO4 dot 10H2O. So what will be Xc? Xc will be molecular weight of NO2SO4 divided by molecular weight of Na2SO4 plus molecular weight of H2O multiplied with 10. Is that clear? Molecular weight of these things. How much molecular weight of H2 Na2SO4? That is 142 divided by 142 plus 180. So you can calculate 142 divided by 0, sorry, 2, 332. Can you calculate and tell me what is the molecular mole fraction here, actually? I think you will be getting 0.44 probably. Yeah. Okay. So you know Xc, you know Xf. Now you don't know Xm. Xm you don't know. You are supposed to calculate Xm. And M also you don't know. So first what will I do? I'll write this balance. F is equal to C plus M. So F is your 320. Sorry, 330. That is equal to M plus C is your 80. Is that clear? This is equation first. What is M? M will be equals to 0, 250. So you have calculated M. So now you can write F into XF, that is equals to M into XM plus C into XC. So F is 330 and what is XF? XF is 0.24, that is equals to M 250 multiplied with XM plus C. C is how much? 80 into XC. XC is your 0.44. So now you can calculate the value of XM from here. Is that clear? So I think you will be getting 0.18. Okay. Okay, so this is all about the crystallizations, and here I have completed your gate chemical engineering syllabus for the gate exam. But again, what I'll suggest you from this point onward, you try to practice as much as question that you can, especially for the gate previous year. So you start the practicing of questions from 1990 and every day try to revise your syllabus, whatever.